Good morning, all. Good morning to one and all present here. Without any further ado, let's enter into the first talk of today. Here, we are having a great opportunity to listen to the words by a great knowledgeable speaker for the first session. I welcome our speaker, Mr. Nacer Chahat, to put light on the topic spacecraft antennas for Earth science and planetary exploration mission. We welcome you, sir. The distinguished chair for the session is Professor A. Unnikrishnan, sir, from QSAT. Welcome, sir. If you have any doubts during the session, just type it in the chat box. Queries would be considered at the end of the session. I would like to hand over the platform to the chair.
Once again, good morning, everybody. And I would like to welcome the speaker of the day, Professor Nacer Chahat, for his, I'm sure that is going to be an enlightening presentation on the topic of spacecraft antennas, meant for exploration of these satellites which are going to explore the other satellites. So let us try to listen to the speaker and understand what best he has got to talk about this special architecture issues which are involved in the design of the antennas for this specific purpose. Over to you, Professor Chahat.
Thank you very much for the introduction. Let me share my slides. I still can't. You guys need to allow me to share the slide. Okay. Okay, so first of all, thank you very much for inviting me here. This is my a pleasure to contribute to this conference. I'm very excited to share some of the latest innovation that we come up with at the Jet Propulsion Laboratory. So this talk will be focused on spacecraft antennas for deep space missions and Earth science. And it will cover a wide range of platforms such as CubeSat, SmallSat, larger spacecraft, rover, and also helicopter if we have enough time to cover everything. I would like to say that I've been blessed and I've been very lucky to work in a place where I'm surrounded with a lot of smart people that allow us to achieve amazing new technologies. Even though space exploration is usually not very risk adverse, we've been lately blessed to be able to infuse a lot of technologies, and that's what this talk will be focused on. One key to be able to do that is not to try to innovate just for the sake of innovating, but innovate to be able to enable missions. So if you bring on the table a new technology that will allow a new type of missions, then people will be welcoming your innovation with their arms wide open. So I will start with one example, which is one of my favorites, Mars Cube 1, which is or was the first interplanetary CubeSat, and not only the first interplanetary CubeSat, this one ventured to Mars and was able to provide band pipe communication during the entry, descent, and landing of InSight lander on the surface of Mars. So this mission came about 5 years ago. Someone came into my office and told me that they needed to find a way to do band pipe communication from Mars, so roughly 1 AU. Band pipe communication means being able to transmit data at the same data rate as you're receiving it. And as you can see here, as InSight is landing, or going into this entry, descent, and landing phase, it's sending a lot of telemetry data to the CubeSat, and the CubeSat needs to be able to transmit the data back to Earth in real time. So at UHF frequencies, which is for short-range communication, we are receiving at 8 kilobits per second, and as a result, this is the data rate that we need to achieve from the CubeSat from Mars, which is roughly a little bit more than 1 AU, which is 149 million kilometers away from Earth. So if you do the math very quickly, knowing that you're limited in RF output power, also because we're limited in terms of DC power, what we needed to achieve was to achieve a gain with an antenna, a gain of 38 dBi with circular polarization. And if you do some very quick maths, you will realize that the size of the antenna needed to be 3 times the size of the CubeSat, which is quite significant. At the time, we didn't have any technology that allowed us to do that because there was no storage volume allocated in this CubeSat. So we had to find a way to deploy an antenna that was 3 times the size of the CubeSat, and yet close the link at this distance. So what we come up with was to use a reflector array, which can fold atop of the surface of the bus of the CubeSat, deploy in a very, very simple way, which is also key for the success of such a mission, and in a reliable way, so that at the frequency X band, 8.45 gigahertz, you have a surface flatness that do not deteriorate the efficiency of your antenna. So knowing all of these constraints, the obvious solution was a reflector array because the panels can fold atop of the surface of the CubeSat. So let's take a look at, oh, the video doesn't work? Okay, well, I guess we're not gonna look at the video. The video just illustrated the InSight communication to this CubeSat, and the CubeSat deploying in space and transmitting the data back to Earth. Oh, okay. Give me 1 second. I might be able to fix this. Oh. 1 second. Okay, we'll do is at the video. Unfortunately, it's not working. Should have checked before. Okay, so can you guys see the slides? Yes? Okay, so like I was saying, the main challenge was actually the storage volume, since we didn't have any volume inside of the CubeSat. So the obvious solution was to come up with a reflectory antenna that actually falls atop of the surface of the CubeSat. You can actually see how it falls, and there is a burn wire that we apply a current into, and then it cuts the wire and the panel deploys thanks to the hinges, spring-loaded hinges that you can see here on this picture. We designed some custom-made hinges so that this panel can fold and deploy without having any gap in between the panels. So as a result, the gain efficiency, the gain is higher and the efficiency is also higher. And also, if you have a gap between panels, your side lobe level will increase quite significantly. So that's the reason why we actually come up with this hinge design to avoid having any performance degradation. So we achieved a gain of more than 28 dBi. We did not use any internal storage volume. And this way, we've been able to close the link with limited RF power coming from the SSPA, and the power is roughly about 4 watts. So you can actually see some important design features here. So the first thing is the panel. So how do we get the surface flatness that we want to survive the trip to Mars, and also not to have the surface bending and because of thermal gradients. And what we did is that we use a stable core in between, and on each side of it, we used a Roger board 4003. And the reason why we use 2 of them is to actually have perfect symmetry. So we even have the reflectory layout on each side. And the reason why we did that was to reduce the thermal gradient. By doing that, you reduce the thermal gradient across the surface of the reflectory itself. So then the optics was another critical thing to come up with. If you design a reflectory without any storage constraints, then it's very straightforward. You can achieve quite good efficiency. But when you have storage constraints, which is what happens when you are actually designed for a commercial product or for an actual application like that, then you need to live with a constraint that do not necessarily allow you to come up with the best design, the best RF design. So the feed was located as far away from the reflectory to have the highest F over D in order to achieve a decent efficiency out of this reflectory. And with these optics, we actually, without changing the pointing of the reflectory itself, of course, you can correct with that by designing the reflectory properly. But here, without doing any of that, we got a pointing of 22.7 degrees, which was very convenient, taking into account the constraint of the UHF antenna, which is located on the other side. And I'm going to talk about that at the same time. So you have the constraint of being able to receive while InSight is landing from the UHF antenna, but at the same time, you need to be able to point toward Earth. And that's the reason why this optic worked out fairly well. And but if we needed to change the pointing, that's also very straightforward to do. As you can see here, this shows you the gain losses. So the computed directivity from this reflectory was around 30.5, and the achieved gain was about 29.4, which gives you about 1.3 dB of loss. And the main contribution is shown here. So obviously you have the feed loss, which is about 0.7 dB at X band, which is pretty decent from a patch array, which is a 2x4 element, circularly polarized. Then you have the dielectric losses from the reflector itself. You also have the ohmic losses, the mismatch loss from the feed, and the losses that are coming from the hinges, because they're taking away some of the area of the reflectory, of the aperture of your antenna. And on the bottom, you can actually see the radiation pattern calculated and measured, and we obtained fairly good agreement between the two. You can see a disagreement between in the cross polarization, which does not drive. Oh, what just happened? What just happened? Can you guys still hear me? I think my
Yeah,
computer
we can
shut
hear
down.
you, but your screen is not there.
Oh, okay. I need to try to restart. I don't know what happened. I'm trying to restart the computer. It just decided to shut off. Okay, while the computer is trying to restart, I will continue talking about the mission. So we launched this mission about 2 years ago successfully. The reflector was deployed right after deploying very near Earth. And from then he did the entire trip with the reflector and the UHF antenna deployed and the solar arrays. We have characterized the radiation pattern of the antenna near Earth to verify that everything was nominal, which it was. We actually got a gain within 0.4 dB from what we predicted. And then 9 months after, when reaching Mars, we communicated and did achieve band-pie communication from the 2 CubeSats successfully. So that was quite an achievement since it was the first time ever. And so we were very, very, very excited with these results. Not only because it was the first time, but also because it's going to pave the way for future CubeSat missions that will come in the near future. So we have about 12 missions that are on the wait list, NASA missions, led by NASA and in collaboration with universities, where we are going to try demonstrate new instruments as well. So we're very, very excited about all of these achievements. So on the back of the CubeSat, we also have a UHF antenna. The UHF antenna is circularly polarized. It's circularly polarized. We're using a loop antenna where we're excited at the 2 corners to get, so to get circular polarization, you need 2 orthogonally polarized antenna, two orthogonally polarization. You need a 90-degree out of phase, and you also need the same amplitude. And so to do that, we excited 2 of the nearby corner of the loop with the same amplitude, 90-degree out of phase, to obtain circular polarization. So that was a very, very clever design that my colleague Emmanuel Descrossas come up with. Okay, the computer restarted. Let me share again. And to test a UHF antenna, you need to do that in free space, in outdoor range, which is capability that we have at the Jet Propulsion Laboratory. Okay. Sorry, I need to log in again. I'm very sorry for the inconvenience.
No issues, sir. No issues. Please continue.
So we did the measurement in outdoor. We obtained very good agreement between calculation and measurement. And I would like to show that to you right now. So I think you need to let me in again. Okay, you need to let me share so I can share the slide.
One second, let me. Okay, you will be able to share your slides now.
Yes. Okay, can you now see?
Yes, yes, sir.
Okay, so this is how we actually achieve the circular polarization. So you have the loop. If you excite one corner of the loop, you get linear polarization in this direction. Then if you excite on the other corner, you excite orthogonally to this polarization. If you put it on the CubeSat at the right lambda over 4 distance, then you can increase the gain by 3 dB. Then if you excite each of these two orthogonally polarized, you will, by 0 and minus 90 degree, you will get the right-handed circular polarization like we wanted. This is how the antenna stow, and this is how it deploys. So it's fairly simple with jack in the box principle, where you have two hinges that deploy the whole thing. To excite with 90 degree out of phase, we actually use a balloon. And what we do is we actually use the loop itself as a ground plane for the strip line. So that's actually another clever way to do that. So kudos to my colleague Emmanuel Descroissas for coming up with this solution. Then for the radiation pattern, this is how we actually measure that on a CubeSat mockup, and you can see the radiation pattern, the good agreement between calculation and measurement. So as you can see, there is a lot of error bar because at UHF, you need to be aware of the accuracy that you can achieve. So that's also, you need to invest time trying to understand that so you don't have any surprises. So this is a picture of Mars that was taken from the camera that's located on the side of the reflectory. So you can actually see the reflectory panel on the top, and you can also see the feed on the bottom. And this, what you see on this figure, is very interesting. So as I said, we had two CubeSats, so two twin CubeSats, Marco A and Marco B. And if you look at the receive power, we have about a minus 145.5 dBm for the first one, and we have about minus 147 for the second one. So you would think that one did not perform as well than the other when you look at that, but that's not quite that. The reason why we had a difference is because the deep space network is using a shared aperture to communicate with two different CubeSats. So one CubeSat was located at the peak of the antenna, and the second CubeSat was located off bore side. And that's the reason why we have a difference in receive power. As I said, we assess the gain to be within plus minus 0.4 dB of what we actually measure on the ground, which was actually super impressive. So we were extremely excited with the result that we obtained, especially for such a challenging mission as Marco. So then, when you come up with a great solution, people usually ping you to come up with even better solutions for the future. So we looked at a larger deployable reflector array for earth science, but also for communication. This one was designed for earth science communication at 35.75 gigahertz, using the same principle, but much more reflector panels to deploy. We achieved 47% of efficiency and a gain of more than 47 dBi out of this antenna that measures roughly 1 meter by 80 centimeters. This is the prototype of the antenna, and you can see the agreement between calculation and measurements. Again, this was a very interesting technology to develop that future missions could potentially use. Now I will talk about mesh reflectors. So the first mesh reflector that we developed from scratch at JPL was actually for the mission called RainCube. RainCube is the first active radar in a CubeSat for low Earth orbit operation. Operates at 35.75 gigahertz. It needed about half a meter diameter with an efficiency of more than 50% to meet the mission requirements. The main driver is efficiency for an active radar as RainCube, because if you lose 1 dB, because it's around, it's two-way trip, you actually lose 2 dB in terms of SNR. So the efficiency was the main driver, and the second driver was the side lobe level. You do not want an antenna with very, very high side lobe levels, so you need to have a good control of the surface that you actually deploy. So we achieved 42.6 dBi out of this antenna and an efficiency of 56%, which is quite amazing at K-band. You can actually see a cross-section of the antenna when folded and when deployed, actually half deployed, not entirely deployed. You can see in the center the telescoping waveguide in blue. You can see the feed horn in the center, which is a multi-flare horn that gives you very similar performance as a corrugated horn. But in that case, they are very, very, very simple to fabricate and also very simple to design as well. It takes you, if you start with rough dimensions that are very near to the goal, you will not take more than 5 minutes to design an antenna like that. And here, one of the main challenges was to find a good trade-off between mechanical and RF. So you want to be able to fold reliably an antenna in the storage volume that was allocated. In this case, it was 10 by 10 by 15 centimeter, so 1.5 U. And you need to deploy it in a way that is as simple as possible. So you need to minimize the number of deployments. So we used a cassette grain antenna. Unfortunately, the video does not want to work. So you have a four screws driving system on 4 of the corners, so 2 here and 2 on the other side, that push the entire ribs and feed horn outside of the canister. Once all of that is out of the canister, you have this bottom hinge that deploys, and then you have the mid hinge that deploys. And you can actually see the mid hinges here in black, and the bottom hinges, you can see them, but they are around here. When this deployed, the feed is released and deployed, and you have the subreflector that deploys with this spring in the center. So we try to keep this deployment as simple as possible, and to minimize the number of deployments, we actually use a cassette grain design because the subreflector is below the focal distance, and that minimizes the number of deployment of the feed. The second thing that's important when you are an RF designer is to try to find a good balance between the complexity of the mechanical design and achieve the highest RF performance that you can. But you don't want to impose constraints that are too harsh on the mechanical design, because otherwise the success, the likelihood of being successful is going down. So you need to have a very good trade-off between mechanical complexity and RF performance. So in this case, we actually minimize the number of ribs. So the maximum number of ribs that we accepted was 30 ribs. And knowing that, we compensated the surface aberration that comes from the fact that between these perfectly parabolic ribs, you have a flat surface. We compensated that by refocusing the subreflector. And you can actually see that very well illustrated in this picture. So what happened is that when you have a surface aberration like this, the focal point is no longer a single point, but it's a region. And you can actually re-optimize for the ideal focal location to get the highest gain out of this antenna. So this is what we did, and we compensated the loss close to almost 0 dB with this number of ribs. So a bad RF engineers would have imposed to the mechanical engineer to increase the number of ribs. And as a result, things would have probably jammed during the deployment. So you need to be aware of this trade-off because that's very important if you want to be successful. So here is a very nice video of the deployment of the antenna in space. So you can actually see the ribs deploying, the mid-hinge that you see here. They are actually constant force spring. And you can actually see a wire here that's located right below the hinges and the mid hinges. The reason why we do that is because during the deployment of these hinges, you don't want one side to deploy before all of the others so that it would stretch the mesh itself. And if it stretches the mesh, then you will never achieve the surface accuracy that you need. At Ka band, we needed about 0.2 millimeter RMS surface. So you need to be aware of these things and make sure that your mechanical engineers are aware of the requirements that you need to meet from an RF point of view as well. So from this picture, you can actually see also the strut that holds the subreflector, and you can also see the mesh. The reason why we took these pictures that we put together to have this very, very nice video is to overlap with a picture that we took, before lunch in the lab. Then, as soon as we received that picture from space, we overlap both pictures to make sure that everything deployed properly. And that's what we did. We were extremely happy with the results since we didn't see any deviation. And here I would like to show you a very, very nice plot of the science. The vertical plot that you see is actually the absorption line provided by RainTube. And the 2D plot that you see is the result that we got from a Nacer CubeSat, which is a radiometer. The radiometer is looking at different absorption line as well. And the scientists, even though the CubeSat were only 5 minutes apart, they overlapped the result and they were extremely, extremely impressed by the accuracy obtained with these two CubeSats. So then, like I said, whenever you get a nice piece of technology, the scientists are always asking for more. So from a telecommunication point of view and also from a neuroscience point of view, people always ask for 1 meter to 3 meters. So we told them on the CubeSat, forget about 3 meters, it's too challenging, you will not be able to do that. However, we could, using a 12U CubeSat, deploy a 1 meter reflector. So we collaborated with a small company, a startup, Tendeg, to develop and qualify this reflector that you can see the deployment on the bottom. So the storage case is shown on the first picture, and you can see the reflector fully deployed on the right. And we have a boom that deploys the reflector itself away from the CubeSat so that you have a fairly good F/D to achieve the mission requirements. So we actually used this reflector to achieve an X and Ka band antenna for telecommunication purpose. And we achieved more than 72% at X and Ka band. and I'll show you some of the results. Those are the feed at X band and K band. Below, you can actually see the model on TCRA grasp, where you can see the CubeSat bus, the boom, and the reflector. And those are the results at X band. You can see a very good accuracy between calculated and measurement. However, you can see that our cross polarization is actually fairly high. You could improve that. It's not too constraining, but for our case, we didn't really care because our uplink, we have so much margin that we didn't want to spend time optimizing that. And you can see that the accuracy between calculated and measured in terms of directivity, gain, and efficiency is excellent. So that shows that these antennas are fairly very reliable after deployment. At X-band, the mesh opening per inch loss are actually very, very small, almost negligible. And the surface accuracy as well is less than 0.1 dB, so you don't need to worry about that at X-band. At K-band, that's another beast. At K-band, the OPI is about the surface mesh loss due to the opening per inch is about 0.25 dB, so you need to account for that. But the surface accuracy is much more significant. We had about 1.1 dB of loss due to the surface accuracy that was about 0.38 millimeter RMS. We think that for a flight version, we will be able to reduce that down to 0.25 millimeter, which will bring the loss to 0.6 dB only. And overall, we still achieve very good efficiency, about 62% efficiency at downlink and 57% efficiency at uplink. And the accuracy between calculating and measurement is excellent because in our calculation in the TCRA grasp model, we included the surface mesh that we actually measured after deployment. So, like I said, I discussed about these very nice demonstration that we achieved using these two CubeSats, the radiometer and the rain tube active radar. And as a result, we are now considering launching a small sat that will fly these two instruments as such with no modification. We will have the radiometer and the rain tube instrument co-located on the small satellites, and we will deploy a much larger antenna for the active instruments for rain tube. This one will be about 1.6 meter, which will allow us to have a much smaller footprint on the ground and as a result, a much better resolution. The trick here is actually to use different feed arranged in a way so that you can have 3 dB of beam width overlap if you take into account for the spacecraft motion. So as you can see, if you look in this direction and move, you will have this 3 dB between this beam, this beam, this beam, this beam, and this beam, which is what you see on the right. And that's where the horn arrangement was critical to do that. And that will allow us to do a map Earth coverage much faster than what we would with a single horn. So that's the trick that the scientists wanted to use to do so. And with this design, we haven't built this antenna and tested it, but we're very confident because as you could see on the two other design, we always were spot on the prediction. So we think that we can achieve more than 70% efficiency at K-band, which each of these horn at K-band, 35.75 gigahertz. Okay, so then we looked at other design, and this one is a small satellite where we're considering flying a solid reflector and a mesh reflector not too far away from each other. And we also want to use a multi-feed to be able to have different beam overlap. In this case, again, using the motion, taking into advantage of the motion of the spacecraft, we can get 1.5 dB of beam overlap. And the trick here was to be able from two different antennas to get the same beam overlap on the ground, so the same footprint. And that's actually what you can see on the bottom here. That's what we managed to do. Despite the fact that we're using a Cassegrain solid reflector and deployable offset mesh reflector, we managed to obtain the same radiation pattern. And that's what you see here. This beam overlap, the solid line is the solid reflector and the dashed line is the deployable reflector. And the way we did that is that first we designed the solid reflector and then we designed the mesh reflector to match the beam of the solid reflector using an optimizer. Then I'm going to talk about metasurface antennas, which is fairly new in the world of space. As a matter of fact, to the best of my knowledge, no metasurface antenna has been flown up to date. And our goal is to launch the first metasurface antenna in the next 2-3 years. So this work has been funded by ESTO through an ACT program. We're very excited by this work because we think that it will open up new opportunities in future missions. So the first one is this flat antenna that has a 3 beam. So we're taking advantage of a quasi-optical feeder, which is called a pillbox, to achieve 3 beam pointing. And all we do is by offsetting 2 feeder horn, exciting a reflector, which is a flat reflector here, we can excite the top layer through these coupling slots. We can excite this top layer and then we can use any type of metasurface on the top layer to get the beam that we want. And so basically this pillbox allows you to get the same amplitude on the top surface, and it also allows you to convert a spherical wave into a planar wave on the top layer. And when you're changing the feed horn, you're actually changing the phase distribution across the top layer. And that's how you're getting this beam pointing change. And I'll show you that in more details. You can see a picture of the prototype on the left. And the metasurface is actually a slot with this pattern. And I invite you to read the paper. Oh, I did not put the reference. I have a reference at the end that I invite you to look at where there is more details and where we explain how to design this metasurface to get the beam pointing that you want. So if you excite feed 1, you actually get a beam pointing at the center. And if you excite feed 2, you get a beam pointing at 45 degrees. And if you excite feed 3, you will get pointing at -45 degrees. And we demonstrated that successfully. As you can see, the agreement between calculated measurements is good, but not that great because the Scilab are getting a little bit high on this side, and that was due to misalignment between the 2 layers. The nice thing about this antenna is that everything was fabricated using micro machining. The bottom layer is made of silicon, and the top layer is made of gallium arsenide. The reason why we really wanted to use gallium arsenide on the top layer is that we could use Schottky diodes to get a full control, 2D control by changing the state of these diodes on the metasurface elements. And by doing that, you can control the beam on one direction. And here is the reference I was talking about that I invite you to read if you want more information about this. The second design was done by my friend David Gonzalez, who was a postdoc at JPL and who's now a CNRS researcher in France, in University of Rennes, where I actually did my PhD. So the reason why we worked on this design is because we wanted to get rid of all the drawbacks of this metasurface. So the first drawback, they are made of dielectric, so they are lossy and they are very narrow band. And also, if you go in an environment where the radiation levels are high, the IESD becomes a problem. And so that's the reason. So if you make it all in metal, you're no longer susceptible to thermal, which is a significant concern when you are made of dielectric and you're narrowband. And so this is the reason why we wanted to make an antenna, a metasurface antenna, entirely made of metal. The reason why this antenna is attractive is that it's completely flat and it doesn't require a polarizer. Polarizer are fairly bulky, take a lot of volume. In this case, we actually achieve the circular polarization with the metasurface itself. We can not only get circular polarization, we can also get linear polarization from these antennas. Everything is included in the reference that I provide in the bottom. Like I said, metasurface antennas have been put aside mainly because they are low efficiency. But with this design, we achieved 50% efficiency at the center frequency. So they are now becoming attractive, and you can find applications where they become extremely interesting, such as lander and rover, where you don't have a lot of storage volume, or even small sats. So this is where you need to come up with technologies, but also find the niche where they fit perfectly. If you can fly a reflector, you would not suggest to have a metasurface instead. You would just fly a reflector. But if you have to fly something that's completely flat, then the metasurface becomes interesting. And as you can see, the accuracy between calculation and measurement is fairly good. And it's not only fairly good because it agrees fairly good, but because of the technique that we use to fabricate it. And the video doesn't work either. But the point of this video was to show you that this antenna was fabricated using additive manufacturing, and it takes less than 5 minutes to fabricate an antenna like this. 5 minutes only. So imagine if you want to fly a very large constellation where you try to minimize the costs by fabricating hundreds of antennas, one after another. This is the perfect technology for this. So just keep that in mind, because those are the things that you need to be aware of. So following the first design that I showed you earlier, where the antenna is flat and we're using a pillbox and then on top a metasurface to get the pattern that you want, we come up with this design, which now is entirely made of metal, operate at 15.5 gigahertz, where we want to have 3 dB beam with overlap between the transmit and receive antenna. So you have 2 feed horn, one that transmits, one that receives, and it's combined to a CMOS system on chip radar that has a technique that in real time allows you to cancel this coupling between the two antennas. So even though the antenna provides about 20 dB of isolation between the feed horn, this technique that is implemented in the CMOS on-chip radar allows you to bring it down by more than 40 dB of isolation on top of that. So it will be 60 dB of isolation. So this is a technology that we've been developing. The antenna has been designed. We still need to fabricate it and test it, and then try it with the actual system on chip radar. And this will fly on a UAV for demonstration. So we're very excited about this, and I hope that we'll be able to share more results in the future. Then I'm going to talk about Europa Lander. Europa Lander is one of the most exciting missions that JPL has been working on, which is a mission concept. We are still in pre-phase A. We have a lot of technology development ongoing to make this mission possible. The enabling technology for this mission was the antenna, because this antenna enables direct link to Earth from the surface of Europa. Why was this enabling? Because initially we were considering sending an orbiter to provide telecommunication capabilities, but the cost of the mission was just prohibitive. So we were asked to look at reducing the cost of this mission by more than twice to be able to make this mission possible someday. And the first answer was, well, the only way we can do that is to do DTE. but everyone thought it was impossible because the requirement to do DTE from the surface of Europa was to design a very large antenna, more than 80 centimeter by 80 centimeter, with more than 80% of efficiency, preferably that does not deploy, because it would be very challenging to deploy in a cryogenic environment. It needs to survive the cryogenic temperature. It also needs to survive the high radiation levels on the surface of Europa, which are something that we've never seen before or never designed against before. And finally, it needs to be entirely flat because we don't have any storage volume. We only can store on the surface of the lander itself because of the landing space. I don't know how to call that. Never mind. And so then we come up with this design that actually meets all the requirements, despite the fact that nobody thought it was possible. We find a way to do it. So this antenna provides dual frequency with circular polarization and provide more than 80% efficiency at both frequencies. It's entirely made of metal. It can survive the cryogenic temperature. It can operate at cryogenic temperature, and it can also survive the high radiation environment of Europa. So when I say survive, the antenna can always survive, but you want to make sure that the antenna is not consistently going to discharge, because these discharges are going to propagate to the telecommunication subsystem, and it will damage some of the hardware, critical hardware. So we design it in a way that this will not happen by making sure that every single component, every single part of the antenna is DC grounded, which reduce the likelihood of IESD events. So the first prototype that we fabricated is an 8x8 subarray. We achieved the aperture efficiency that we needed to achieve. So when I define efficiency, let's be clear about this. This is the ratio between realized gain, so that includes all the losses, over the maximum directivity that you can get out of the aperture of the antenna. And we got more than 80% with this efficiency definition. And you can see that the agreement between calculated and measurement is perfect. Then comparing this technology with what has been used before, so on MSL, they achieve about 50% efficiency. On NER, 25% efficiency at uplink and 50% efficiency at downlink. But those will not survive the environment of Europa because they are mainly made of dielectric. And then this one, which is a radial slot array, which is the one that you see on the bottom, achieved, that was the baseline for this mission initially, achieved 37% efficiency at uplink and 18% efficiency at downlink. And that's the reason why we thought that DT was not possible. And as a result, our antenna allow us to be smaller, less mass, relaxes the pointing requirements, and allows us to handle much higher power. And as a result, you can combine it with a tweeter, a 100-watt tweeter at X-band, and be able to achieve much larger data rate. So if you go from 25 watt SSPA to 100 watt a tweeter, you get 6 dB of improvement there, on top of all the other gain improvements. So this is why we're pushing for this subarray for future Mars mission as well. So then we built a 16x16, which consists of 2x2 subarrays put in an array, and the array, the 2x2 subarray array, are excited with waveguides. So the waveguide is dividing from 1 to 4 ports. And here is the agreement between calculated and measured. The efficiency that we obtain on the first prototype are still very impressive. And the agreement between calculated and measurement is just very impressive. You can barely see the difference between the two. So this shows you how the antenna actually falls on top of the surface, and then it deploys with the gimbal, and the gimbal will be pointing toward Earth. Yeah. And finally, we fabricated a 32 by 32, and we measured. And as you can see, we also obtained a very good accuracy. We qualified the antenna by doing ISD measurement, TID, testing. So we basically put it in this vacuum chamber where we go to cryogenic temperature and we bombard this antenna with electrons. And we do that so that the 3 mission life of total ionizing dose are being reached. And also we make sure that the rate of charging is the same as the real mission so that you can simulate what the ISD discharging and the rate of discharges that you will see. And we did not see any discharge, or the only discharge that they have seen, they couldn't tell if it was only noise or if it was actual discharges. So that tells, and that was actually the first time ever that they tested a piece of hardware and they see such low discharges, and that's why they couldn't tell if it was noise or not. So our antenna is ready to go to Europa. We reached TRL6, which stands for technology readiness level. And whenever we go into a flight missions, we want to be at TRL6 to move forward with the technology. This is a nice picture of the Europa lander. Here you can see the actual antenna that I was just showing that we tested, so that you have a good scale idea. And also here you can see the landing legs. These legs allows the lander to land on any type of topology. And so we don't expect the surface to be perfectly flat. And so we need to be able to land on chaotic surfaces. And that's why our mechanical team is working on that as well. And they are making a lot of progress in order to reach this TRL6 grail. I think I'm running out of time, so I'm probably gonna skip quite fast. This is a mission, surface water and ocean topography, which is a Earth.
You have,
yeah.
You have time for 15 more minutes because we have.
Okay.
Next session is at 11 o'clock our time, half an hour later.
Okay, perfect. Thank you. So this mission is an Earth science mission. It's a very, very large spacecraft for which we have done a lot of work, and you will see an example of this work. So we have developed a telecommunication antenna that provides dual polarization, which allow us to communicate with 2 different polarization at the same time within 8.025 to 8.4 gigahertz bandwidth. So we have 2 ports that goes into a polarizer. Each of the ports provide different polarization. One is right, the other one is left polarization. This antenna was designed to operate on a very crowded nadir deck where there is 2 large reflectors. There is the altimeter that you see here. There is the radiometer that you see here that would cause strong multipass, and a strong multipass that will generate interferences. And then the antenna also need to have a very good cross-polarization discrimination, because the cross-polarization of one polarization to another will actually be additional interferences as well. So the requirements are that the XPD needs to be more than 20 dB at 60 degree off-bore sites to minimize cross-polarization losses. And we also need a very rapid roll-off after this 60 degree off-bore site, so that we don't have multipass or strong multipass contribution. And that's why past 90 degree, we need to be less than minus 15 dBi of gain. So we designed this antenna, which is externally corrugated horn, and combined with a polarized polarizer. Like I said, each port provides the two polarization. And you can see here at the 60 degree that we get a very good cross-polarization discrimination, and that's what we see on the bottom. So if you look on the bottom, we have in free space, we have more than 25 dB of cross-polarization discrimination. Once you do that, you still need to verify that the performance are met on the spacecraft and across the temperature. So we tested the antenna from minus 100 to plus 100 degrees Celsius. And we simulated the performance on the spacecraft using TICRA-GRASP, where we modeled all the key elements that could contribute. And you can see that the XPD still met at 60 degrees of both sides. That was a very stringent requirement that was successfully met by developing this antenna. And we didn't have a lot of time to come up with this design. It was less than a year. The design, you need to come up with a design that shows that it works very quickly. It's less than a month. And then to get to a prototype would be about 6 months, more or less. And then we had a flight hardware that was fully tested within a year and a half. Again, publication below, feel free to take a look at it if you want more details. So here is actually a video of the spacecraft deploying the large deployable antenna, which is a reflectory, and it's very high power. And so we did a lot of work to make sure that everything will work properly, since we have a very high power being radiated from the radar toward the Nacer deck. And I'm not going to go into the details for that, but here I wanted you to have a grasp of the complexity of the deployment. It's K-band, so the surface deployment needs to be excellent. The deployment accuracy needs to be excellent, and everything needs to be extremely stable because this is an interferometer, so the phase accuracy between these two antennas needs to be very good. Okay, and now I'm going to talk about the Mars helicopter. So for the Mars helicopter, we designed the antenna on the helicopter itself and also on the rover. And I'm going to show you how we made sure that the link will close with these two antennas and the process to do this. So first, in real life, you have constraints that you really don't have in the academy world. So I really want people to be aware of this constraint that we have when we design these things. So first, the ground plane that we have on the helicopter is very small. So we actually have a ground plane where we used as a reflective surface is the solar array. And that was the only way. That's the only option that we had. So because the ground plane or the reflective surface is asymmetric, you will have a cross-polarization component that looks like this. So it's not ideal. And then if you account for the blades that are made of carbon fiber, it's also a very good reflective surface at 900 megahertz, which is the frequency of operation for the telecom subsystem for the helicopter. So when these blades are rotating, the cross-polarization will also be affected. As you can see, the gain remains fairly the same, but the cross-pole keeps moving. So you need to account for that when you're looking at the link budget. On the rover gave us the worst spot on the rover. And as you can see, the ground plane is even smaller, but we had to deal with it. So, okay. So we have a monopole antenna that we made bulky enough that it would survive the launch vibration and shock requirements. And as you can see, because of the multipass and the shadowing of all of these components on the rover, the gain is not great. The gain can be fairly low in some directions, and the cross pole is not great either. So you need to account for that in your link budget to have a proper account of the polarization loss. So V polarization is what we're using. H polarization is the cross pole. this is the map that we have when the helicopter is on the ground, when it's landed. And this is when we will transmit most of the images back to the rover. We can achieve 250 kilobits per second in the dark green spots, and we can achieve 20 kilobits per second on the light green spots. The center diameter, the center circle has a diameter of 250 meters, and the outer circle is 1 kilometer diameter. Most of the communication is going to happen within this 200 meter diameter. And so in average, we will be fairly good in most cases. In the worst case scenario, which we never designed for, it means that we will have the worst case alignments between the helicopter and the rover, and the blades will be in an orientation so that we have the worst polarization losses. You can see that in some spots we might lose communication. So we need to be aware of that, so that if that's the case, we know what to do. We can just spin the blades, or we can rotate the rover if needed. And when the helicopter is flying, there is no problem at all. You can see that the link is no problem. We can close the link within 1 kilometer without any issues in most cases. By the way, average cases is more than 90% of the case. So you need to be aware of this statistic when you are making an assessment as well. And that's the reason why we never design for worst case. Otherwise, that would just not make any sense, and the cost of the mission would go up very, very quickly. So we went and we did a field test where we have two mock-ups, the mock-ups for the rover, where we have the EM antenna, and on the other side, we have the helicopter mock-up. We placed it about 200 meters away, and we compare the measure results. We actually, you see the platform that's under the rover, we actually rotated it to do an assessment of the radiation pattern as well. So we could assess how the pattern of the antenna on the rover will affect the receive power. And we've never seen anything worse than the worst case prediction, which is exactly what we wanted to see. And you can see that we were never lower or on the average case most of the case. So that means that our link budget assessment was actually very, very good. So to conclude the talk, I have listed a few publications that we have in the literature published in the past 5 years. So I invite you to take a look at them if you're interested in this topic. We also have this month a publication that was released on the Mars helicopter on the topic that I was just presenting. So feel free to take a look at it, where you can have more insight on how we actually perform all of this calculation. And to finish, I have a book that's coming up early 2021, published by Wiley, which is entitled CubeSat Antenna Design, which I invite you all to get a copy. And I think there is a lot of interesting content where we try to convey all of how the requirements are flown down to the antenna team, and how the antenna team is working with the system team to actually work this requirement to come up with the simplest antenna design and the most robust mechanical design deployment, providing the best RF performance in taking into account all of the design constraints that we have. So I cannot emphasize enough how important it is to work very closely with the mechanical engineers and also the system engineers to work these requirements, to have a better trade, try to negotiate this requirement where it's possible. So I always say a good antenna engineer is an excellent system engineer. So don't close your bubble just into your expertise. You want to understand how telecom system engineer works. You want to understand how the radar also works, so that you can work with the system engineer the requirements because they actually don't understand what your constraints are. So those are the trade-off that you need to work as an antenna engineers to get the best out of your missions. So thank you very much for your attention. Now I would like to open to questions. I apologize for the issues that we had early on, and I hope there is questions that I can answer.
In the chat box, we could take it.
Well, the session is now open for discussion. Questions are invited from the audience.
Sir, there are a few questions in the chat box. Would you please answer them?
Okay.
Okay, let me see if I can. I don't think I can see the chat while I'm sharing.
If someone could read the questions, then it would be good.
Yeah.
Sir, there is a question on the second or third slide talking about Marco X-band deployable reflected array. And the reflect array has two patch antennas on both sides of stable core material. Why do you need two patch arrays instead of one?
Sorry, repeat the question about Marco. You said,
Yes, sir.
why is there? Yeah, please repeat the question.
So there is a question on the second or third slide talking about Marco X-band deployable reflected array. And the reflect array has two patch antennas on both sides of stable core material. Why do you need two patch arrays instead of one?
Okay, I think, so just to be clear, a reflector array is not a patch array. They do look like patch array, but it's not. It's a resonant element where we change the size of them to change the phase across the surface of the reflector. So that's saying the reason why we have the reflector on each side, the same pattern, is from a thermal point of view. If you have a perfect symmetry on the reflector surface, you reduce the surface gradient across the surface. And so the surface will not bow as much. So that's the reason why it's very important to have something perfectly symmetrical.
Nacer, this is Sudhakar.
Yep.
Yeah, the question is from my side. So if you have two arrays
Yep.
with a stable core, instead of that, why can't you use one reflector array and increase the stable core size? It reduces your cost, I believe, cost and mass.
Yeah, so we actually looked at that. That's exactly what I was saying. So we look at different options. One option was to make the composite larger, but if you do that, the surface is still going to bow much more. So that was the trade-off that we found in terms of better surface flatness and mass. So we actually went through this trade-off early on. Yeah.
Okay, thank you.
Hello.
Yep.
Say the array which you showed for say I think 16 by 16 possibly of a microstrip array, which is from the metamaterial side. Okay, towards the end. See there you have a slot at the center of each of those patches. Are they really meant for only increasing your bandwidth, or it's for your specific
okay. Yeah.
you're looking for?
Is the E-plane.
Yeah, excellent question. So the element here is actually excited on these bottom points, and we have on the center here we have a post that allows us to be directly in contact with the ground plane. So everything is in metal and holds against each other thanks to this post in the center. It's located in an area where the current is very close to zero, so it does not interfere with the RF of the patch elements. But then the shape, the reason why we have this slot is to get the circular polarization at 2 frequencies.
Yeah, that's so. Yeah, that's an important thing. I see. So this when this is already flown or is about to be.
No, so that design was, we started working on that 2.5 years ago, I think, or maybe 3 years ago. We reached TRL-6 now. So now we're ready to fly it for future mission. We specifically developed that for the Europa Lander mission concept. And we brought it to TRL-6 for that purpose. But now we realize that this antenna has a lot of features that are advantageous compared to the antenna we're currently using on rovers and lander on Mars. So we're trying to infuse this antenna in future Mars missions as well.
Now, you were trying to qualify this at cryo temperatures also. So do you just
it has been qualified.
and then do the measurement?
So the way we qualify over thermal is that there is different type of tests that we do. There is a thermal cycling test where we verify that the antenna is surviving. So we have survival range. We have, sorry?
It will be passive during that time.
Yeah, for survival, it's passive, but for operational, we're actually checking the S parameter of the antenna. In that case, for the Europa mission concept, since we wanted to check the performance of this antenna at cryogenic temperature, which is lower than -170 Celsius, we're actually doing a radiation pattern measurement at cryogenic temperature as well. So we're putting that in an enclosure, foam enclosure that will not interfere with the RF performance, and we will use liquid nitrogen to go to this cryogenic temperature. And in real time, we'll get the radiation pattern and gain of this antenna. That's how we're qualifying to.
This is a great setup for making the measurements for this particular one. I think it will go a long way.
Exactly, because
getting such type of antennas for future missions.
Yep.
Yeah. So thank you very much. This is Mahadevan from ISRO.
Thank you. Thank you.
Thank you.
Sir, there are a few more questions in the chat box. How do you choose which polarization to use when designing a spacecraft antenna?
So it's pretty straightforward. For telecommunication, it's always circularly polarized. For space to Earth, because we don't want to be impacted by the orientation of the spacecraft. If you have linear polarization, you need to make sure that the transmitting antenna and the receiving antenna are lining up. So you don't want to be dependent on the polarization. And circularly polarized is also less sensitive to rain, for instance. For the science mission is driven by science. So usually the scientists tell us what are their polarization requirements. Sometimes they want V and H at the same time. More rarely, they want V and H, and then they combine to get circular polarization as well. Sometimes they want circular polarization, but it happens much less. For the Mars helicopter mission, we use linearly polarized because it was more convenient for near-range communication, and especially in an environment where we have a lot of multipass and shadowing. So that's the reason why we used linear polarization.
Thank you, sir. So there's another question. Is it possible to design antennas at high frequencies such as terahertz range?
To design any antenna or a specific antenna?
I think the question, the question was just asking about any antennas. Is it possible to design?
Oh, yeah, of course. We have designed and fabricated a lot of terahertz antennas. I invite you to look at Dr. Gautam Chattopadhyay's work, where he has extensively published on terahertz instruments, including antennas. Most of the time they use horn antennas, multi-flare horn are very convenient at terahertz frequencies because you can just drill and make arrays of them. And then there is other design that are entirely micro machine antennas as well. So they do horns, they do metasurface antennas as well. The one that I was just showing with entirely made of metal. We made one, David Gonzalez designed one with, he called it the fakir bed antenna. It's made of post, where the height of the ground below the post changes. There is a lot of antenna solution at terahertz, but you need to be cognizant of the losses that you will incur with the different technology that we use. And that's why horn antennas are usually the best way to go for terahertz antennas.
Okay, sir.
Next question.
Sir, could you please comment on the transmission power and directivity used by ground stations to communicate with satellites, especially when dealing with interplanetary missions and even interstellar missions like Voyager 1 and 2?
Oh, yeah. I'm afraid I'm going to give you the wrong number. Yeah, I wouldn't venture give you the numbers. I don't exactly remember the gain of the antennas, but most of our deep space network antennas operate at X-band and K-band. And for Voyager, since the Voyager is so far away, our division consistently try to improve the performance of the DSN. And I know that they've been working very actively into increasing the high power amplifier outputs. And I can't remember, I think it's 20 kilowatts, but I can't remember for sure. So I invite you to double check the number of where the state of the art stands for. All of that are readily available online. So feel free to check the JPL website where all of these numbers are shared.
Okay, sir. So the next question is, what is the application of helicopter versus rover on Mars?
Oh yeah, good question. So the purpose of the Mars helicopter is a technology demonstration. And in this case, the team that actually come up with this technology wanted to demonstrate that we are capable of flying on the surface of Mars. And the reason why it's so challenging, it's because the density is 1% of the one of Earth. And to be able to fly on the surface of Mars, you need to generate much more lift. So the RPM of the blade is much higher compared to the typical helicopter that we're using on the surface of Earth. So as a result, the helicopter is limited in terms of mass. So the constraint was 2 kilograms. So every subsystem that delivered to the helicopter had very, very strict mass allocation, and it was non-negotiable. There was very limited margin allocated for the subsystem, and we knew that if we exceeded this 2 kilogram requirement, we would not be able to fly on the surface of Europa, on the surface of Mars, sorry. And so that, yeah, so the goal of Mars is to go on Mars, land, fly, and demonstrate that we're capable of doing these flight maneuvers. And that will be a success for the Mars mission, and eventually will open up for future helicopter mission on the surface of Mars that will perform science. And we're looking at different instruments for future Mars helicopter missions, so that we could launch a constellation of those on the surface of Mars that could bring their own science. That's the end goal. Next question.
Sir, what is the material of reflector used in rain cube? It seems translucent.
The material used? Is that the question?
The material used in reflector in rain cube.
Yeah, so these reflectors are mesh reflector. So they are very similar. Actually, I don't have a picture. That would be interesting to share a picture here. You can also see it here. you can see it a little bit better, but they are mesh which are gold plated, and we pick the opening per inch of this mesh to be as reflective as possible at the frequency of operation. So at K-band, we tend to use 30 opening per inch or more. On RainCube, we managed to use 40 opening per inch, but those type of mesh are much more difficult to find. So that's why on this 1 meter reflector, we revert back to 30 OPI. Yes, Sudhakar.
Yeah, the material is gold-plated molybdenum.
Yes.
Yeah.
Yes.
It's about 1 mil in diameter. Hey, since you're on that RainCube, you have you showed the half-meter deployable reflector. Can you go back to this? Looks like it has a large FOVD. I don't know what FOVD you are using.
No, the F/D is 0.5.
Yeah, that's a lot. So don't you think reducing FOVD will simplify the feed deployment?
I think we discussed about that on one-on-one. That's actually a very good question that people ask me all the time. So
what's the
Dr. Rao is saying that Dr. Rao is saying that if you used a lower F/D, then you would have the subreflector much more lower, and you wouldn't need to deploy the subreflector. So that's his argument. However, if you do that, then the reads are going to be, the curvature of the reads is going to be much more significant, and you will not be able to make everything fit into this small canister. And that's a very good question, because that's actually the first thing that we looked in when we did a trade study to see what could fit and what should we be doing in terms of optics to minimize the number of deployments and come up with the best optics for this antenna. And that's ultimately the one that we picked. And in this paper that I provided on the bottom, we actually spend a lot of time explaining all the trade-off and how we came to this optics and why we picked a Cassegrain antenna.
Okay, thank you.
So one more question. When is your book is going to be released?
Early 2021, but it's already in pre-release, so you can already pre-order it.
Okay, thank you, sir. We are extremely thankful to you for sharing your deep knowledge about this topic with us, and your session was full of enthusiasm and knowledge. Thank you, sir. I also
thank you very much, and again, I apologize for the technical issue. Thank you for your patience.
Thank you, sir. I also thank the distinguished chair of the session, Professor A. Unnikrishnan, sir, for his valuable presence. Thank you.
May I add a few sentences? May I have few views from my side?
Sure, sir.
In fact, it has been a very wonderful presentation. He took us over a wide range of topics. And what really attracted me was the perfect sort of precision by which the results were presented. The temperature cycling, for example, is something which I think is just really mesmerizing for me. I'm quite surprised that you can have that kind of facility for cycling the temperature of such a large range, which I think my colleague from ISR also was quite appreciating that. Also, what I attracted is that the academicians have to work in line with the systems engineers. I think there was a mention from Professor Chahat that is necessary. I think that throws light on the fact that the academic community has to work closely in association with the system engineers so that you can fabricate and produce the proper technology, the right kind of products out of the technology that is being developed. So overall, it has been a very wonderful presentation, and we are really thankful to you for the excellent amount of, for the large amount of technical material that you could provide us. So it's only proper that we need to know about the full biodata of the presenter, which I could not present at the beginning. I'm sorry for that. For the conference organizers, full biodata of this to be wind up. Could you do that? Hello?
Yeah,
Yes,
no
sir.
problem.
Yes, sir. Yes,
Can they do that? Kindly give the full biodata of the speaker before we wind up.
Yes, sir. Because
Well, I could not do
there's
that
such
at the beginning. I should have done it, but because I wanted to start the whole session and was eager to listen to the speaker, kindly do that now.
Yeah, sure, sir. Because it is such an impressive talk, and it's so impressive because we see that he's so young and inspiring the youngsters who are attending the program. Dr. Chahat completed his master's and PhD from University of Rennes in 2012, and he's a senior antenna engineer with NASA, as we have seen. And he has got 4 books to his credit, several patents, hundreds of articles and conferences and journals. And as he mentioned, his new book is on the line. And he has been awarded, co-invented and award-winning rain cube mesh reflector antenna is being used. And he's recipient of several other awards like CST University Publication Award, 2011 Best Paper Award, and NASA Early Career Achievement Medal Award, and so many. The list is very long, and it is shared in the website. So I'm sure we'll be hearing more of you in the future. And thank you so much for accepting our invitation to present during our APSYM 2020. Thank you again. Thank you, Unikrishnan sir.
Thank you. Bye.
Thank you. I request all the panelists to switch on the video to take a screenshot.
Thank you, sir. Thank you, everyone. Now we are entering in the first technical session of today, which is based on antennas. There are 6